I am Bindusree, working as an assistant professor in the Department of Electronics and Communication Engineering at Institute of Aeronautical Engineering. Today, we'll discuss about these codes. What is a code? When numbers or letters are represented by a specific group of symbols, the digital data is represented, stored, and transmitted as a group of bits. The group of bits is called the binary codes. So generally in the binary codes are the two types. One is the numeric code, another one is the alphanumeric code. Again, in the numeric code is divided into several types of codes: weighted code, non-weighted code, self-complementing code, sequential code, error detecting and correcting code, reflective codes, and cyclic codes. Coming to the alphanumeric code, again it will divide into the two types: ASCII code, ABCDIC codes. Okay. First one, we'll discuss about this. What is weighted binary code? So in the weighted binary codes, that codes are depending on the position of that particular weighted stands. So that is called the weighted binary codes. So generally we are taking the any number. That number is the decimal number system. So here we are taking the one example. So that is the 3, 4, 5. So here each and every bit. So it is depending on that particular weight of that position. Okay. So this 345 is there. So this 5 is the first position, 4 is the 10th position, and 3 is the 100th position. So depending on that position we are representing, so that is the ones or hundreds or thousands or whatever it is. Okay, so this is the weighted binary code. So it depends on the position of that particular weighting standards. Okay, so next one is non-weighted binary code. So it does not follow the positional weighting standards. Means, so here if you are taking the any number, so that is not depending on the particular position of that weight. So that is the non-weighted codes. So non-weighted codes examples are XS3 code, gray code. Okay. So coming to the weighted code examples are 8421 code, 2421 code, 5211 code, and BCD code. Binary, decimal, binary, coded decimal. Okay. So first one we'll discuss about this 8421 code. Generally in the binary values are follow this 8421 code only. Why binary values are follow the 8421 code? We'll see that one. So here the weights are the 8421. All the weights are positive weights. So this is called the positively weighted code. Here all the weights are the positively weights. So it is called the positively weighted code. So this code is also called the BCD code. Okay. So how we are writing the binary values? By using the 8421 code. Okay. So now I want to write this binary values. First we are adding all the position of that weights. So here the 8421 is there. So now adding all the bits, 8 plus 4 12, 12 plus 2 14, 14 plus 1 15. Now we are taking the decimal values from 0 to 15 only. Okay, so how we are writing the binary values depending on this 8421 code. Okay, so let us see 8421. Okay, so this is the binary values. So this one is the 2 power 0 value, 2 power 1, 2 power 2, 2 power 3. 2 power 0, 2 power 1, 2 power 2 and 2 power 3. Okay, so now I want to write the binary values for this decimal values. So this is the decimal number 0, 0. So here it is not depending on the any position of these weights. All the values are the zeros only. Next one is 1. So now I want to write the binary value of this for 1. So here this position of the weight 1 is there. So take this particular position. So remaining bits are the zeros. Remaining bits are the zeros. So next one is the 2. So here directly we are having the second position. So taking that one is the 1. Remaining bits are the zeros. Coming to this 3. Now I want to write the binary value for this 3. So 2 plus 1. 2 plus 1. 3. So taking these 2 positions, that's what here we are writing the 1. Remaining bits are the zeros. Remaining bits are the zeros. 4. So directly we are having this position 0, 0, 0. Next one is 5. 4 plus 1. 4 plus 1. So 1, 1, 0, 0. 0, 1, 0, 1. Next one 6. 4 plus 2. 6. 7. 4 plus 2 plus 1. 1, 1, 1. 0. Next bit is the 8. So directly we are having this position of this weight. So 1. Remaining bits are the zeros. In the 9. 8 plus 1 is 9. First one and this position and this position of this one. So 0, 0. Similarly 10. 8 plus 2. 8 plus 2 is 10. 1, 1, 0, 0. Like this, we are writing the binary values for each and every decimal value. So, in this 8421 code, if we are writing the any binary value for that decimal number, so only one possible condition is there. So that's what BC binary values are follow this 8421 code only. Okay. So next one is the 2421 code. Here the weights are the 2421. This code has all positive weights. This code has all positive weights. So that's what this is also called the positively weighted code. Here the weights are the 2, 4, 2, 1. Adding these bits 2 plus 4, 6, 6 plus 2, 1, 8, 8 plus 1 is the 9. Okay. So now we are writing the binary values only for 0 to 9. Okay. See 2, 4, 2, 1. First position is the 0. Now all the bits are the zeros. Next one is the 1. So this first one is the 1. Remaining bits are the zeros. Next, second position. So here the weights are the 2421 is there. So now I want to write the binary value for this 2. So either we are taking this position of this weight and either we are taking this position of the weight. So for one decimal value, we can write the 2 possible binary values. Either we can write like this 1, 0, 0, 0. So here we are taking this position of this weight. So that's what here we are writing the 1. Remaining bits are the zeros. Otherwise 0, 0, 1, 0. Either we can write this way or this way. That's what in the binary values are not follow this 2421 code. Why? Because it might be the confused. Either we can write this one or this one. But coming to this 8421 code, so we are writing this only one way of that one. That's what in the binary values we want to write the any binary value follow the 8421 code only. Coming to this 2421 code, so we can write this each and every value. We can write the 2 different possible conditions. So, okay. So either we can take like this one or this one. So now we'll take this one. Okay. So next bit is the 3. Next decimal value is the 3. So now add the 1, 1. So 2 plus 1, 3. Remaining bits are the zeros. Next one, 4. Fourth bit directly we are having the 4. Otherwise 2 plus 2, 4. Okay. So directly we are having that position of that weight is the 4. Take that one. Remaining bits are the zeros. Next 5. 4 plus 1, 5. Next 6th bit, 2 plus 4. Either we can add these two or either we can add these two. So already for this two, we are taking this position of this weight. So that's what I will take these two positions, 1, 1, 0, 0. Next one is the 7. So 2 plus 4, 6 plus 1, 7. Next 8. 2 plus 4, 6 plus 2, 8, 0. 9. 2 plus 4, 6, 6 plus 2, 8, 8 plus 1, 9. This is the 2421 code. Okay. So this 2421 code is a self-complementing code. So this self-complementing code provides the 9's complement of a decimal number and ones and zeros equal to the 2421 representation. So how 2421 code is a self-complementing code? So these all are the decimal values. For these decimal values, we are taking the 9's complement. So what is the 9's complement? We are taking the any decimal value, subtracting with the 9. We are getting the one resultant value. So that is the 9's complement of that particular decimal value. Okay. So let's see. So first we are taking the 0. Apply the 9's complement of this 0. 9 minus 0. So we are getting the 9. Similarly, 9 minus 1. So our decimal value is the 1. Apply the 9's complement of this one. 9 minus 1 is the 8. Next one, taking the second one. Apply the 9's complement of this one. 9 minus 2 is 7. Next one, 3. 9 minus 3 is 6. Next we are taking the 4. Apply the 9's complement of this one. 4. 9 minus 4 is the 5. This is the 9's complement of a decimal number. Okay. So within this truth table only, we are applying the 9's complement of that particular decimal value. We are getting the resultant. So coming to this one, coming to this condition, binary values. So here we are applying the 1's complement of this one. Again we are getting the same results are in this truth table. So then this is called the self-complementing code. Okay. So what is the 1's complementing? So the 1's will change to the zeros. Zeros will change to this 1's. Okay. So first one is all zeros. First we are taking the all zeros. So zeros will change to this one. 0 will change to this one. 0 will change to this one. 0 is changed to this one. So satisfy this 1's complement of this one. So next we observe this one. Second, first and 8th. Okay. So in the first bit of this one, 0, 0, 0, 1. Apply the 1's complement of this one. 1 will change to zeros. Zeros will change to 1. 0 will change to 1. 0 will change to this. So here we are observing this one 1, 0, 0, 0. So 1, 1, 0, 1 is there. So here we are taking the position of this weight is the 2. So let us take this one. 0, 0, 1, 0. Now we are observing this 2 and 7. So zeros will change to 1, 0 will change to this one, 1 will change to this zeros, zeros will change to this one. Okay. Again this 1's complement is satisfied. Next coming to this 3. Coming to this 3. So here for this 2 we are taking this position of this weight. So for this 3 also we are taking this position of this weight. 2 plus 1 is the 3, 0, 0, 1, 1. So now observing this 3 and 6. 0 will change to this one, 0 will change to this one, 1 will change to this 0 and 1 will change to this 0. Okay. So next one 4 and 5. 4 and 5. So either we can take like this. So 1 will change to 0, 0 will change to 1, 1 to 0, 0 to 1. So observing this one. So either in the 2421 code, each and every decimal value we can write this two ways. So if you are taking the values depending on this particular truth table, so we are applying the ones complement of this one, we are getting the same result in this particular truth table only. Then, so 2421 code is a self-complementing code. So if we are apply the nines complement of this particular decimal value, we are getting the same result. We are apply the ones complement of this one, we are getting the result in this particular truth table only. So then 2421 code is a self-complementing code, but it is not follow all the binary values. Why? Because each and every decimal value we can write the two ways of that particular binary values. It might be the confused. So that's what here in the 2421 code is not followed for writing the binary numbers, binary values. Okay. So next one is the 84 minus 2 minus 1 code. So here also the weights are the 8, 4, minus 2, minus 1. So in this particular weights, combinations of the positives and the negatives are there. So this is called the negatively weighted code. So this is also the self-complementing code. Okay. So 8, 4, minus 2 and minus 1. So now add all the position of these weights. 8 plus 4, 12, 12 minus 2, 10, 10 minus 1, 9. So here also we are taking the 9 bits only. So 8, 4, minus 2, minus 1. So taking the decimal values zeros. So first one all the bits are the zeros. Okay. So next one is the 1. Next one is the 1. For this one, for this one. So here we are not having the any position of the weight directly. So that's what for this one. 4 minus 2, 2, 2 minus 1 is the 1. Okay. 1, 1, 1, 0. Okay. 4 minus 2 is the 2. 2 minus 1 is the 1. So now we are taking this 3 positions. Okay. Next one is the 2. 4 minus 2 is the 2, 1, 1, 0, 0. Next, third bit. So 4 minus 1, 3, 1, 1, 0, 0. Next one is the fourth bit, 1, 0, 0, 0. Next, fifth one, 8 minus 2, 6, 6 minus 1 is the 5. So 1, 1, 1, 0. Next one is the 6. 8 minus 2, 6. 1, 1, 0, 0. Next one is 7. 8 minus 1, 7. Next one is 1, 0, 0, 0. Next one is the 9. 8 plus 4, 12. 12 minus 2, 10. 10 minus 1, 9. Okay. So this is the truth table for 8, 4, minus 2, minus 1 code. Now apply the ones complement of this one. So first all the bits are the zeros. Apply the ones complement of this one. 0 will change to this ones. Okay. Next one is the 0, 1, 1, 1. So zeros will change to this one. 1 to 0, 1 to 0 and 1 to 0. Next 2. 0, 1, 1, 0. Zeros to 1, 1 to 0, 1 to 0, 0 to 1. Next 3 and 6. Observing the 3 and 6. Zeros to 1, 1 to 0, 0 to 1, 1 to 0. Next 4, 5. Zeros to 1, 1 to 0, 0 to 1, 0 to 1. So it satisfies the ones complement of this one. So that's what 84 minus 2 minus 1 code is also the self-complementing code. Okay, next one is the non-weighted code. It does not depending upon the positions. So it is not assigned any fixed value. It is not depending on the position of that particular weights. So examples of the non-weighted codes are the XS3 code, gray code. So first, let's see the XS3 code. So in that particular name only, we are having the definition. So XS3 code. Whatever the binary value we are taken, so we are adding the 3 bits in that particular decimal value. Then we are getting the resultant value. So that is the XS3 code. So it is not depending on this any particular weights. So this is a unweighted code. Okay. So XS3 code is a adding the 3 in that particular binary values. So that is the XS3 code. Okay. So first one, we are taking the binary values. So generally we are taking the 3 bits of that one. So B3, B2, B1 and B0. Similarly in the XS3 code, E3, E2, E1 and the E0. So this first bit is the LSB bit, this is the MSB bit. This first bit is the LSB bit, this one is the MSB bit. Okay. First we are taking the 0, 0, 0, 0. 0th one. This is the decimal value. Okay. So now I want to the XS3 value for this 0. So what we are doing? Adding the 3. 0, 0, 0, 0, 0, 0, 1, 1. 1, 1, 0, 0. So the bits are the 0, 0, 1. For the decimal value 0, the XS3 value is the 0, 0, 1, 1. Means it is not depending on that position of that weight. Next one is the 1, 0, 0, 0, 1. 0, 0, 0, 1. Okay. So 0, 0, 0, 1. So what we are getting? 1 plus 1, 1, 0. 1 plus 1, 1, 0, 1, 0. So this is the 0, 1, 0, 0. For the decimal value 1, we are getting the 0, 1, 0, 0. So next one, 2, 0, 0, 1, 0. Adding the 3 bit, 2 plus 3 is the 5, 0, 1, 0, 1. Next one is 3, 0, 0, 1, 1. For the decimal value 3, the equivalent binary value is 0, 0, 1, 1. So now I want to the XS3 code, add the 3. 0, 0, 1, 1. 3 plus 3 is 6. 6 equivalent binary value is the 0, 1, 1, 0. Next 4. 0, 1, 0, 0. 4 plus 3 is 7, 1, 1, 1. Next 5. 0, 1, 0, 1. 5 plus 3 is 8. 6, 0, 1, 1, 0. 6 plus 3 is 9. Similarly 7, 0, 1, 1, 1. 7 plus 3 is 10, 1, 0, 1, 0. Like this. So 0, 1, 1, 1. Adding the 0, 0, 1, 1. 1 plus 1, 1, 0. 1 plus 1 is the 1, 0 plus 1 is the 1, 1. 1 plus 1 is the 1, 0, 1, 0, 1, 0. So for the 7, we are getting the 1, 0, 1, 0. So here it is not depending on the position of that weights. So XS3 code is a unweighted or non-weighted code. So this is also the self-complementing code. So first we are writing the all the binary, all the values from the 0 to 15. Then we are apply the ones complement of this one in this particular XS3 code. So then it satisfy that ones complementing. So XS3 code is a self-complementing code. Okay. Here we are writing the values only for the 7. So if you are writing all the values from the 0 to 15, then apply the ones complement of that XS3 code truth table. Then it satisfies that one. So XS3 is a self-complementing code. Next one is the gray code. So gray code is also a non-weighted code. It is not depends on that particular position of that weights. Okay. So gray code is a unit distance code, cyclic code, and reflective code. Gray code is a unit distance code, cyclic code, reflective code. Why gray code is a unit distance code, cyclic code, and reflective code? First, we are apply the gray code for this all the binary values based on the truth table. We'll discuss the why gray code is a unit distance, cyclic, and reflective code. Okay. So this is the truth table for converting the binary to gray code. So how the binary values are converted to the gray? So this is the procedure for converting the binary to gray code converter. Generally in the binary to gray code conversion, so how we are apply the XOR gate for this binary to gray code conversion. AB are the inputs. Output is the A XOR B. A bar B plus AB bar. So 0, 0, 0, 1, 1, 0 and 1, 1. Okay. So A equal to 0, 0 bar is the 1. So B equal to 0. So A equal to A bar B plus AB bar. A equal to 0, 0 bar is the 1, B value is 0. So A equal to 0, B bar is the A equal to 0, B bar is the 1. So 1 into 0 is 0, 0 into 1 is 0, 0. So next one is 0, A equal to 0 and B equal to 1. So if A equal to 0, A bar is 1, 1, B value also 1. So A equal to 0 and B bar is 0. 1 into 1 is 1, 1. So A equal to 1, B equal to 0, 1. A equal to 1, B equal to 1 is 0. So when both the inputs are same, that output is the 0. When both the inputs are different, that output is the 1. So we'll remember the XOR gate truth table. So now how the binary code is converted to the gray code conversion. So first we are taking the 4 bit of this binary values B3, B2, B1 and B0. Okay. So in the right side of this bit of this position is called the LSB bit, least significant bit. This B3 is the most significant bit. If we are converting the binary to gray code converter or gray to binary code converter, so whatever the MSB value is there, as it is we are writing the same MSB value for converting the binary to gray or gray to binary. So that is the G3. Next, apply the XOR gate for the adjacent bits. The adjacent bits are the B3 and B2. So apply the XOR gate of this one. So we are getting the G2. So next one, B2 XOR B1. Next, apply the XOR gate for these two adjacent bits, getting the G1. Next one, B1 XOR B0. So that is G1. This is the procedure for converting the binary to gray code conversion. So let us take the one example for converting the binary to gray code. So B3, B2, B1 and B0. Okay. So the value is, if you are taking the 1101. So this B0 is the LSB bit. This B3 is the MSB bit. For converting the binary to gray code converter, whatever the MSB value is there, same value is right here also. So B3 value is the 1 is there. So that is the G3. Okay. Next, apply the XOR gate for these two adjacent numbers. 1 XOR 1. 1 XOR 1. So in the XOR gate, we are apply the same inputs of that one. We are getting the output is the 0. So that is the G2. Next one, B2 XOR B1. 1 XOR 0. So here the inputs are the different. Two different inputs, output is the 1. So that is the 0. Next one, B1 XOR B0. 0 XOR 1. So two different inputs, that output is the 1, 0. Okay. So this is for the converting the binary to gray code conversion. So similarly, gray to binary conversion. Gray to binary conversion. So that inputs are the G3, G2, G1 and G0. So this is the least significant bit. This is the most significant bit. Least significant bit, most significant bit. So here also, so whatever the MSB bit is there, as it is, we are writing in the same value in the binary value. So G3, B3. Now we are apply the XOR gate for the resultant value and the adjacent number. Now we are apply the XOR gate for the resultant bits and the adjacent number. That means B3 XOR G2, we are getting the B2. Next, we want to the B1 bit, apply the XOR gate for the resultant bit and the G1. B1. Next one, B1 XOR G0. That is B0 value. Okay. So we'll see the one example. 1011. 1011. So G3, G2, G1 and G0. Okay. So as it is, we are writing the B3 value 1. So next, apply the XOR gate for the B3 and G2. 1 XOR 0. So when different inputs are there, that output is the 1. Next one, 1 XOR 1. When both the inputs are same, that output is the 0, B1. B1 XOR G0. 0 XOR 1. Different inputs are there, that output is the 1, 1, 0. So this is the truth table for converting the binary to gray code conversion. Okay. So now, how the gray code is a unit distance code. So if you are taking the any two subsequent values, so for this truth table, if you are observing this any two subsequent values, that unit distance is the 1, then it's satisfied. So if you are observing these two, so first two bits are 0, 1, 0, 1 same, 1, 1 same, only the second bit is the changing, 1 will change it to this 0. So here the distance is the unity. Next, we are observing this one. 0, 0, 1, 0, 0, 1. 3 bits are same, only 1 will change it to this 0. Next, we are observing this one. So first two bits 1, 1 same, 1, 1 same, only 0 will change it to this 1. So here the distance is unity. Next one, 1, 0, 1, 1, 0, 1, same one. So only 0 and 1 is changing. So if you are observing this any two subsequent values, for example, if you are observing these two subsequent values, 1, 1, 0 and 1, 1, 0, same, only 0 will change it to this one. So here the unit distance is here the distance is unity. So that's what gray code is, a unit distance code. Okay, so it satisfies the unit distance code. Okay, so next one is how the gray code is a cyclic code and reflective code. So first we are observing this first bit of these positions. So first one is we are taking the 0 and the second one we are taking the 1. So if we are not concentrating on remaining bits, only observing these zeros and ones. Okay, so next coming to this next bits. So only here we are observing the only 2 bits. Here we are observing the only 2 bits. So second bit is the 1. Second bit is the 1. So this 1 is reflected here. This 0 is reflected here. Okay. Only this MSB bit is the 1. This 1 is reflected here. This 0 is reflected here. Now we are observing the third bits. So third bit is the 1. So up to this third bit is the 1. Next third bit is the 1. So now we are observing this one. So 1 0. 1 0 is reflected here. 1 1 is reflected here. 0 1 is reflected here. 0 0 is reflected here. So here we are observing this 2 bits. So that's what here we are taking the 0 1 and 0 0 also. Okay, up to this. Okay. Next we are taking this fourth bit of this one. Next we are taking this fourth bits of fourth bit. All the fourth bits are the ones. Okay, now observe this one. So here the 1 0 0 is there. So that 1 0 0 is reflected here. 1 0 1, 1 0 1, 1 1 1, 1 1 1, 1 1 0, 1 1 0 reflected here. 0 1 0. So that will be reflected here. 0 1 1 reflected here. 0 0 1 and similarly 0 0 0. So within this truth table only same bits are reflected to next bits. So that's what gray code is, a reflected code. As well as the bits are writing in the cyclic way. So the gray code is a cyclic code. Thank you. So in this session, we'll discuss about the weighted and non-weighted codes.
Like, share and subscribe. Hit the bell icon for more updates.